everyone. In this video, we are going to continue our exploration of Lewis structures and structural, how do we get a structure, by looking at this idea of structural isomers. So let's consider a molecule made of two carbon atoms, 6 hydrogens and 1 oxygen, so C2H6O. And if I look at this structure, C2H6O, right, sorry, there are two different but equally valid Lewis structures that I can draw based on this molecular formula, right? I can draw a structure where I have the two carbons connected in a line, an oxygen, hydrogen connected to the oxygen like so, and then the other 5 hydrogens are connected to carbon, right? Or I can draw a structure where I put the oxygen in the middle, right? And then I have all of the hydrogens are bonded to carbon, oxygen in the middle like this. So if we look at these two structures, both of these structures give everything an octet. Both of them have the right number of electrons. Neither one of them have any formal charge. So both of these structures are equally valid. Now, the question I have for you, are these the same molecule? Well, what do you think? Looking at it, no, they're not, right? Because these atoms are connected together in a different way, these are different structures, which means that they're different molecules. And in fact, they have very different properties. This molecule over here is called ethanol. And this molecule here is dimethyl ether. Ethanol is the alcohol that we drink. It's an alcohol. It's got a boiling point of about 78 degrees Celsius, can form hydrogen bonds, interact really well with water. Dimethyl ether, on the other hand, is pretty volatile and has a relatively low boiling point, highly toxic, etc. So these are two molecules that have the same formula, same composition, same molecular formula, but different structures. And when that happens, we call those things structural isomers. So ethanol and dimethyl ether are structural isomers. They're isomers of each other in that they have the same formula, but different structures, right? So a structural isomer are molecules with the same composition, so the same molecular formula, but different structures. And remember that different structures means different properties, because as we've talked about before, structure determines function. Structure determines properties. So if the structure is different, the properties are different as well. So C2H6O has two structural isomers. Both of those things are fine. They work. Okay. So what if I have a molecule like C2H4O2? How many ways do you think I can draw this molecule? How many Lewis structures do you think I can draw? Well, I don't know. Pause the video. Draw as many as you can. Right? Take a few minutes. Draw as many as you can. Pause the video. And then when you're ready, once you have a few structures, we'll move on. Okay. So if you looked at this C2H4O2, you probably came up with some very different structures. Off the top of my head, I'm going to draw a couple out, right? I put the carbons in a row. I'm going to put an oxygen here. I'm going to put a double bond here. This is one that comes to mind, and then I have these 3 hydrogens, right? I could double bond the carbons here, right? I can put oxygens here like this, single bonded to that. Essentially, any structure that you draw here where you have a double bond, I can put an OH on one carbon, and then I can put 2 hydrogens and then a double bond oxygen on another carbon, like so. There are so many different ways that I can draw this structure. And this is just 3 of them. I think that you probably came up with a couple others. There are some others other than the 3 that I've drawn here. Life gets more like, how do I know which one of these I'm talking about when I say C2H4O2? And then what if I get a larger molecule? Like what if I get C6H12O6? Holy crap. That is a lot of different structural isomers, right? The thing to keep in mind is the number of atoms in the structure is increasing. The number of different ways that you can draw those, that you can connect those things together, increases exponentially, right? It increases by a lot. And in fact, if I look at this C6H12O6 molecule and look at different numbers of isomers, I'm not even going to count because it's just, oh my God, it's just so many different possible isomers. So essentially, C6H12O6 is a useless formula for me because, and for us now, because we don't know how those atoms are connected together. And remember, it is the structure that determines the properties. It's how those things are connected together that I'm paying attention to, and that's what I care about. So how do we get some more information about how those things are connected? For large organic molecules, you'll often see things written in what we call a condensed structural formula. And a condensed structural formula really just gives us information about how those atoms are connected. And to help us out, we're going to go back to C2H4O2. Now, let's say that here with this structure, what I'm really talking about is I'm talking about acetic acid. So acetic acid is one possible molecule that has the molecular formula of C2H4O2. If I write it as C2H4O2, that doesn't tell me I'm talking about acetic acid because remember, that can represent any of at least those three and several other structures that we didn't draw. Okay, so let's see if we can make this give us a little bit more information. If I pull out one of the hydrogens, that at least tells me that one of the hydrogens is acidic. So HC2H3O2 gives me a little bit more information, but not as much as you might think. But I can draw, what I can write is I can say, okay, acetic acid has a CH3. The structure for acetic acid looks like this. This is the molecule that we drew that had the CH3 here, C double bond O, O, H. This is the structure for acetic acid, right? So if we connect this to this, I have a CH3, that's connected to a carbon, that's connected to an oxygen, another oxygen, and a hydrogen. So I have a carbon connected to an oxygen, another oxygen, and then that hydrogen is connected to, and then that oxygen is connected to a hydrogen. So CH3COOH is what we call the condensed structural formula for acetic acid because it tells me how those atoms are connected together in space. Okay, it tells me what's connected to what. Oftentimes you'll see formulas for organic molecules represented this way if the structure is not drawn out. So some other examples, like for example, this guy right here, what this tells me here when I have these things in parentheses is that there's two of these CH3 groups attached to that carbon. So I have a carbon here in the middle that has a CH3, a hydrogen, and then a chlorine attached to it like that. And put my lone pairs on my chlorine, and you can span out the CH3 groups to be 3 hydrogens attached to that carbon. For this guy here, right, I have a CH3, so I have a CH3, so C3 attached to a carbon, that's attached to a hydrogen, that's attached to that should be a 2, CH2, so CHH, and then an OH up there. And then that's attached to a CH2. And then that's attached to a CH3. So what this tells me in the middle, parentheses in the middle, tells me that there's a branch. Parentheses at the beginning, like this, tells me that there's more than one. Okay, this tells me that CH2OH group is branched off of this carbon, so it's not in the line. It's not continuing in the linear part of the structure. These get easier to read as you do some more practice. A couple things to keep in mind and to recap when we talk about structural isomers, what we're talking about are molecules that have the same molecular formula, but they have different structures and they have very different properties. Structural isomers are different molecules. They are different things. Condensed structural formulas can give us information about how those atoms are connected. And there is a ton of practice on Canvas with going from a condensed formula to a structure and then going from a structure to a condensed formula. So take a look at those practice problems. Please come in and ask questions. I hope you've noticed that it's getting really, really annoying to write these things out. And in class, we'll go about a way to shortcut some structures. Okay? Have a good day, and I will see you all in class.